Good afternoon from NOAA's Climate Program Office. My name is Ned Gardner, and I'm your host today. This is the second of two webinars exploring inland flooding in the Mississippi and Missouri River basins that is ongoing this year. The first webinar addressed some of the forecasting and modeling tools that are being used and developed to better understand floods of this magnitude. That webinar was an Earth system science and modeling perspective, and today's webinar, we're also taking a broad view, but particularly thinking about socioeconomic perspectives, both on impacts to the basin and in the basin. Addressing this event specifically, the watershed as a whole, and looking broadly at flood management. So that first session is available as a recording online. I've put a shortened URL on screen so that you can find that first recording. This session is also being recorded and will be archived at the second URL that you see on the screen right now. You can also visit the news section of cpo.noaa.gov to find both of those pages. You'll have to scroll to load a second set of results to find these webinars. And if you have any questions, of course, you can reach out using ned.gardiner@noaa.gov. I'll put that in the chat panel in just a moment. I'm going to mostly stay out of the way today, but I'll be monitoring the questions panel on the right hand of your screen, and I'll use that to pose a question or two, or as many as we can fit in within the 15 minutes allocated to each speaker. If we don't get to your question, we'll attempt to answer it either by answering in the questions panel by typing in the answer, or we'll follow up with an email. So today we have four excellent speakers, and we're going to get things started with Dennis Toti from the U.S. Department of Agriculture. He's going to be speaking on wetness and impacts on Midwest and Plains agriculture. I'm going to hand over control to you now, Dennis.
All right, thank you very much. Appreciate the invitation, and I'm happy to be talking about this issue. It has been a very difficult year here in the Midwest and Northern Plains, and it is an ongoing one because the issues that existed in the spring and carrying on the last fall are carrying over and impacting agriculture as we go along. Ned, I just want to check and make sure you can see my slides, correct?
We can see and we can hear you loud and clear. Thank you.
Excellent. Thank you very much. I also apologize if there's any noise that comes in the background. There's work being done in our building right now. They're grinding concrete, so I will get random loud noises as we go along. Again, I'm Dennis Toti. I am the director of the USDA Midwest Climate Hub. We have been front and center this year for dealing with the issues related to the wetness and cold that have widely impacted the Missouri River and Mississippi River this year. I'm going to give you a quick background on the hubs. I'm going to do a quick review on the climate because there's several factors that have impacted agriculture specifically, and then we'll touch on the agricultural issues going on here. First picture is the classic of this year from Hans Schmitz and Purdue Extension, an irrigated as a center pivot irrigation sitting in the middle of a flooded field. That is classic for this year. Just a brief background on people not familiar with the hubs. There are 10 hubs nationally. They were created just over 5 years ago to deal with climate issues in agriculture, specifically climate change in agriculture. This year has become is one of those more extreme issues that we have been we've accepted and dealing with that. We officially cover an 8-state region, Minnesota, Missouri, over to Michigan and Ohio, but because of some long-standing connections and the extension of the corn and soybean area out of the Northern Plains, which lays over very, very much with the upper Mississippi and Missouri, we deal with issues related to both of those areas. Just a quick background on the agriculture of this area for people who may not be familiar with it. The big part of the upper Mississippi and upper Missouri are the main corn and soybean growing areas. And we're not talking sweet corn here, this is field corn. This is data from 2013. Basically, excuse me, on a county by county basis, the darker green the area it is, the number of acres that are planted to that crop. So lots of soybeans are grown from the eastern Dakotas into Ohio and then down along the Mississippi River. Corn over much of this area, not quite as far south as soybeans are dead center here. Also, you have winter wheat extending and other small grains, spring wheats, rye, sunflowers that are grown out in the northern plains area that are also part of this region. And then you have various areas of hay and alfalfa that are grown for feed. And just a reminder, a large part of the soybean and corn are used for animal feed, in addition to the small amounts that are used for human consumption. Also related to this, the only issue was not flooding this year. We had some major storm events in March and April, including the bomb cyclone in March that people heard about. That several of these events were major winter storms, and during the springtime, that is a time when there's active calving, that livestock are having young, and when these occur in the middle of snowstorms, that's a very detrimental problem for them. It's very difficult for ranchers. Heard many stories of ranchers sleeping in vehicles waiting for calves to drop in the middle of snowstorms, trying to capture them because they cannot be exposed to that serious an issue for that long a period of time. So just a quick larger issue on the agricultural issues. We've been talking about Mississippi, Missouri River. The direct flooding on the Mississippi and Missouri River did impact agriculture somewhat. It's limited shipping for getting grains that are being delivered because the river was shut down. That was not delivered. There was also fertilizer that was being brought in. There were some loads of fertilizer did not make it in time to be put on fields because, again, the river was shut down. And then the bomb cyclone, there was a lot of flooding there that did impact areas in Nebraska, and there are some places along the Missouri River. There's where the Missouri River bottomland is there's a very productive agricultural area, but last year and again this year we've had widespread flooding, and we'll show you a couple graphics on that overall. So a little bit of a quick climate background. The issues were not only this spring, they extended back to last fall, largely impacting our area. Our spring this year, average temperature ranks, again, this is a bone to NCEI here, some graphics from them. South Dakota was the 9th coldest spring on record. States all around in the upper 30s or so. Interestingly enough, as we went east to Ohio was on the warm side. In fact, they had record early last freezes this spring, but you'll see as we go along, they had planting issues as we went along here. The wetness was also a big player this spring, but extending further back. These are ranks of statewide precipitation ranks for May through or March through May, this 3 months of the spring, ranking top 10, Kansas wettest on record, several states, Nebraska to Missouri, wettest on record in May. And then if we extend back the last 6 months, December to May, and then going back to last June, these were the real players in this whole situation. Wetness extending back to the December and even back to last fall. These 124s, wettest 12-month period on record for these states. And just as a reminder, what happens when you are wet the previous fall, soils tend not to dry out, so you're preset for problems this spring. So we knew we were going to have issues going into the spring already, and then the wetness of the spring added to that situation. The only state around here that was not quite as bad, Missouri, we had carryover drought issues, and then North Dakota had dryness that they missed out on a lot of the precipitation that occurred this spring. And this extended all the way out to the East Coast. Astoundingly wet conditions all through this area. So again, soil moisture going into this is late May soil moisture, a NOAA product on modeled soil moisture. The bluer it is, this is in millimeters, the wetter the soil is compared to average. The lower right-hand side here, we have data from the leaky bucket model from the NOAA's Climate Prediction Center, and the percentile ranking, the darkest green is the 99th percentile, saying we're in the top 1% of wettest soils modeled over the last 100 years. And that really laid out our situation for how wet. And what is the problem with wet soils? One, they warm more slowly. Colder temperatures are colder already. Wet soils don't warm up as quickly. It slows field work. You can't get out and get work done. It increases disease chances in crops. And if it's excessive, which it was, we lose nutrients out of the soils. So what happened in the way of crop progress this year? This is a graphic from a colleague of mine, Laura Edwards. This was from this spring. This was not crop from this year. This was corn that was planted last year and was not harvested, sitting in rain from this spring. And that's kind of what we've seen overall here. These graphics are USDA NASS crop progress on where we were in late May. Corn in the lower left-hand side, soybeans in the upper right-hand side. The top number in each state was the percent that was planted of each of these by this point, and then the bottom number is where they were behind. And you'll see that especially here in corn and soybeans, we had numbers where we were 50 to 60% behind, not actually planted, but behind average where we were supposed to be. So very slow. It was the slowest corn bean planting on record by this point, and the second slowest on soybeans. Over the last, this is data going back to the mid-90s that we have this record. So we're very slow, very late getting out here. And when you're late, you don't get much progress going on in the growing season. Our main areas of damage this year, these are indemnities, crop indemnities from RMA, the USDA's risk management agency. The darker areas, indemnities of over $10 million, and that is only the damage done so far, not where we are going ahead. That areas of the eastern Dakotas, northern Illinois, northwest Ohio, and then this area along the Missouri River where they were flooded and there was no chance of being able to get any kind of a crop planted. The season progressed slowly. As we moved along, we did not make up progress. Here's where we are, soybeans by this most recent week. Again, very delayed. The red line here shows where we are compared to previous years. We're neck and neck with 1996 for the slowest soybean development on record. Dropping leaves is mature soybeans. We're at 55%. So we have 45% of the soybeans in the soybean area that are still susceptible to freeze damage. We're not going to get a freeze yet, but we still are susceptible to some damage until we can get this crop to mature. Corn, same kind of situation compared to 2009 for latest developing. Only 43% is mature nationally, 30% behind, so that's 57% that is still susceptible to freeze damage should it freeze. So we're still waiting for when that first freeze because we've been delayed so far for the growing season. So some larger issues that come along with this when you're late planting or into wet planting. You're delayed in planting phenology, slow crop development. We would have had a great growing season this year if we'd planted in normal conditions, but because we were so late, we never really caught up. And actually, September did help us catch up some, but we're still behind. Disease issues when you're dealing with crops in wet conditions, weed issues because you're not able to plant crops in a certain time frame. Part of the way of weed control is the crop can grow at canopies and then keeps weeds from forming because they don't get any sunlight. Weeds were able to get ahead of the crop, so we have weed issues. And then the wetness and cloudiness, we've had a lack of sunlight, kind of been an issue. And then the delays, when you delay crop late enough, you start getting into crop being mature for freeze, and then we're gonna have lots of high moisture corn, very immature corn, or corn that we just can't do anything with. So that's kind of been our situation as we're going along here, the larger situation that we've been dealing with. And that wraps up my part of this.
Thanks so much, Dennis. I really appreciate the overview. You mentioned the leaky bucket model from CPC, and I hadn't heard that term, so could you elaborate what that means?
No.
Okay. No worries.
It's a fairly simplistic water balance model, as I understand it. It doesn't go through all the detailed processes, but it ends up basically doing a balance between rainfall and then evapotranspiration, and I think it's called a leaky bucket because it does allow some water to move out of the soil moisture profile somewhere along the way. I don't know many about the detail of it. It's overall a pretty decent model to give you an idea of general conditions. It doesn't give you detailed soil conditions.
Fair enough. Okay, I understand. One thing that was occurring to me as you were speaking was that with all these delays in planting and then the slow developments going to harvest and harvest being lower than typical, I wonder how the ongoing dispute with China factors in terms of markets, and whether in fact some of the trade disputes have brought in subsidies that have allayed some of these impacts.
I don't know how much I can talk about this since it's not my area of USDA, but it has been a very interesting year from a decision-making standpoint. And the reason for this is when we were so late getting planted this spring, the indemnities I showed are part of crop insurance called Prevent Plant. Basically, it's if you're too wet to plant, you get a settlement. You don't put out inputs, you don't plant, you just get a settlement, and then you have to manage weeds and whatever through the year. Early or late, as the spring progressed, that was probably going to give people's best option, given where we were with markets, where we were with prices, that people could just say, I'm going to get a settlement, I don't have to worry about a crop, harvesting, marketing, any of that kind of stuff. Then markets started to react, realizing that there was going to be probably some limited crop this year, and then we also got into the money that was going to be given for the trade settlements. The first hints of that were around, so that changed the decision-making process of many people, and it became a very tough decision because. When commodity prices were good, you want to try to grow as much as you can because you can make money. Commodity prices are not good right now. It's very difficult to make money because of the commodity prices. So it's a struggle to try to get through in this situation. So what we've had on a weather and climate standpoint this year has added on top of other commodity and marketing issues that people have seen.
Thanks, appreciate that, and thanks for putting up the URL. I know you do a lot of work with Doug Cluck, who's going to be speaking later, and that you use a lot of the products that NOAA produces on climate. So we appreciate your collaboration. We're going to go ahead.
No, I was just going to include one of the things that we do is to deal with some of these issues is we do a monthly webinar in conjunction with Doug, and Doug can talk about that more if he wishes, but it is how we help provide climate services here in the Midwest, is this collaboration among climate service providers using USDA, NOAA, and partner products. Excellent.
So folks can tune into that, and if they have questions, of course, reach out to us. I'm going to hand over the presentation to Sam Munoz from Northeastern University. He's going to be speaking on how humans have altered the flood event frequency in the basin from a much longer time perspective. So we're really glad to have you, Sam. Take it away, and thank you for being here.
Sure, yeah, thanks for inviting me. I'm going to talk about the human angle to things as well as sort of a climate angle as well. Can you hear me, Ned, and can you see my slides?
Yes, both.
And can you see my point?
Yes,
oh,
I can see your mouse.
And do you see Dennis's webcam?
Yes, no. I see Dennis's webcam.
Huh.
I don't know how to make that go away.
I'm gonna just.
There's a hide webcams button at the top of your screen if you.
There.
But I can see full screen your presentation.
Okay, great. Okay, so I'm going to be talking today about work that my colleagues and I have been doing that's looking at the role of both climate variability on flooding across the Mississippi Basin, especially in the lower Mississippi. I'll talk a little bit about other parts too, as well as the role of sort of recent, from a geologic perspective, human activities, particularly channelization, changing land cover, changing properties of the floodplain, et cetera, on flood hazard. And, you know, floods happen frequently, but even within the historical period, we just don't have that many events that we can really use to understand some of this. Like, our sample size is small. And so to increase our sample size, I'm using a technique classic in geology, which is to basically just extend our time scale. So we're basically going back in time, and we're going back in time using both model simulations that simulate events over 1,000 years or so, as well as reconstructions from sediments and tree rings and proxies like that that tell us about flooding over the last 500 years or so. All right, so there we go. So the 2019 floods are just sort of the most recent flood event as part of, within the Mississippi Missouri Basin, right? These events have been occurring and affecting people as long as people have decided to build permanent structures next to the river, right? So this is just the latest in a string of what I would call sort of perennial disasters, and they continue to be disasters in part because, while our ability to forecast is getting better, we still are regularly caught off guard by these kind of events, just like what just happened, and it's still happening this year. So, how do we improve that? So one thing that we've been looking at is this idea of climate variability, and particularly oceanic forcing of floods, and what in the climatology community are called pluvials, so very wet periods. There's been quite a bit of work done in this field lately that's looking at the role of oceanic forcing, particularly ENSO in the Pacific, and to a lesser extent the North Atlantic, in forcing drought in the mid-continent, in central North America. And so we've been looking at extending that kind of work to thinking about pluvials and floods. And so on the left here, I'm showing you a map of the correlation field between soil moisture in PDSI and the Niño 3.4 index. So Niño 3.4 index is just the index that we use for whether it's an El Niño or La Niña event. And what this is showing, and the little dots here, the little dots here are showing that this is a significant correlation, right? And so what we're showing here is that over the much of the western part of the basin, during El Niño events, we have much higher soil moisture. And that's a significant relationship. And this is over the historical period, so going back to like 1948 to 2016 or so, right? The correlation between those two. On the right here, I'm showing the flood event frequency at different stations along the Mississippi Basin. So what I mean by flood event frequency is just how many floods, in this case we're saying a 2-year event is a flood, have we observed at that gauge within an 11-year moving window. So it's just a count going through. And when we look at that, we see that, the lower Missouri at Herman, the upper Mississippi at St. Louis, and the lower Mississippi at Vicksburg, seen here in the lines in red and sort of dark red and orange, are all sort of moving together, right? Those are all highly correlated, which is what we expect from this map, right, on the left. And then the lower Ohio at Louisville is really kind of doing its own thing, right? In fact, it's basically out of phase with everything else, which is interesting from a hydrologic perspective that I won't get into. But in essence, there seems to be some pattern here where these tributaries and parts of the basin, the western part of the basin, are all sort of in phase, and the eastern part of the basin is sort of out of phase. We've looked more specifically at the relationship between floods, especially on the lower Mississippi and ENSO. That's what I'm showing here on the right. So again, we expect that there's some relationship here between soil moisture and flooding on the lower Mississippi. So let's look at that. So let's look at a few specific events. Upper left is 1927, and then 2011, 73, and 83. And the red is the Niño 3.4 index, where the red and blue chart is the Niño 3.4 index, where red are El Niño events and blue are more sort of La Niña-like conditions. And the black and gray are just river stages at Vicksburg and Memphis. And so what we see in all these cases is that preceding these flood events, it could be a few months, it could be 1 or 2 months, it could be 6 months, it could be 12 months. But in all cases, we had an El Niño event before. There's a lag time though between the height of that El Niño event and the peak stage of the flood. And that lag seems to vary in time. right? And so this is only 4 events. We can look at other events too, and this pattern generally holds, but we just don't have a very big sample size. And so what Sylvia D and I did, Sylvia D's at Rice now, she's a modeler. We looked at the CESM Last Millennium Ensemble. So what this is CESM running from 1850 to 2000, so just over 1,000 years, running 10 times. And CESM does a pretty good job of simulating ENSO and its teleconnections, and it has this particular run has this. It also simulates river discharge for big rivers like the Mississippi. And so we started playing with this and playing with that output and seeing what was there and seeing if there was some relationship, if we really increase our sample size, if that still holds. And the short answer is that yes. So on the left here, we're just looking at peak annual discharge simulated in over the lower Mississippi Basin in La Nina or neutral years in gray, and in El Nino years in red. And our sample size is quite big, 11,500 years. And there's the significant difference, right? Discharge is generally bigger in El Nino years, generally smaller, not El Nino years. We can go ahead and go and calculate the actual, we can do flood frequency analysis, calculate the recurrence intervals. And again, when we do that, we see this big difference between the recurrence intervals for El Nino years versus sort of La Nina neutral years. So that if we look at what is a 100-year flood in sort of any given year, that magnitude is actually only a 20-year flood in an El Nino year, right? When we sort of probe this model a little more to understand what's going on here, we just looked here on the left. We're looking at just the top 1% in terms of magnitude of all the simulated floods. That works out to 115-ish. 100-year-ish floods, and we're looking at here time to peak discharge on the x-axis in months. So 0 is the peak discharge month, and we're going back in time and forward in time after that. And so what we see consistently when we average all of those events out, again in the simulation, is that preceding these events we have El Nino-like conditions. We have a slight increase in precipitation, which is consistent with what the teleconnection is over lower part of the basin. And over that time, we're gradually building up soil moisture. And then just in the month or two before the event, maybe the month before the event, we see a big precipitation event, much like the sort of bomb cyclone or some of these other big precipitation events that tend to trigger these floods that is triggering this event. And so we think of this as sort of a two-phase process. We have this sort of priming where we have El Nino conditions that come in and gradually increase soil moisture. And then we have this sort of a spark, where the spark is just a big precipitation event that's coming in and really delivering a lot of precipitation. And because soil moisture is so high, of course, that water's nowhere to go but the channel, right? But that's what the model says. I tend to not trust only models. I think models only as good as our understanding of the processes and what the data say. And my training is in geosciences, and so of course I wanted to go out and do field work and collect data. And so a lot of my time has been spent developing these paleoflood records. For now, we published some work on the lower Mississippi, and we're working now on doing this kind of analysis on the Missouri, the Arkansas, and the Ohio. But what we're essentially doing is going to lakes, to depressions in the floodplain, and we're vibrating these 30-foot long aluminum irrigation pipes into the bottom of those ponds and collecting records of sediment accumulation in the bottom of those ponds. And that sediment that accumulates in the bottom of those is really useful because we think they're providing us a record of when floods occur, and also we can infer how large those floods were as well. So I'll sort of walk through how we think this works. Here's one of our sites, Lake Mary in Mississippi, on the lower Mississippi. It's this oxbow here, very pretty looking horseshoe shape. And so what we think is how this works is that during normal conditions, non-flood conditions, the river's flowing downstream, it's doing its thing. And there's some maybe hydrologic conductivity between the lake and the channel. And there's some maybe fine sediment that's exchanged between those two, but we're not going to exchange coarser material, bed load and coarser sediments between that channel and the lake during these times. But then when we have a big flood event, these oxbows really basically become part of the channel again. And when they become part of the channel again, suddenly they're going to start receiving bed load and moving that bed load through them to some extent. And so what we end up with is these sort of, when a flood passes, we end up with these sort of bands of coarser material that we think are related to flooding. So here, when we first went to Lake Mary, this is when I started this project in 2015, 2016. Lake Mary was the first site we went to because I knew that it had this sort of modern connectivity between the channel and the lake. When we got there, we knew we were probably in the right spot because all the houses that are there are up on these stilts. So here on the left is my two field assistants standing next to a house on stilts. And we could see on some of the houses that hadn't been repaired yet, and what landowners pointed out to us, you could see the flood line from the flood of record, which was 2011. That was still very obvious on those houses. And sure enough, when we core these lakes, on the right, I'm showing you just the top 20 centimeters from what we collected from this lake of sediment. The core we got from here is 9 meters long. That represents about 200 years, which is really, really high sedimentation, which is nice, although challenging to work with. But what we see in just the top 20 centimeters is on the left here, we're looking at a radiograph, so just X-rays through the core, and then we're looking at grain size, so the texture of it, and then on the very right, XRF, and the ratio of zirconium to iron is often used to infer grain size. So the black line and the red line are kind of the same thing. And what's it showing? It's showing that we have these two bands in these upper 20 centimeters that are coarser grained, right? These two little layers. That upper one, and to date these, we're throwing all kinds of different dating techniques at them, lead-210, cesium, OSL, radiocarbon, and sort of throwing those all into an age model and using those to estimate the ages of different depths. And when we do that, that uppermost band is very likely the 2016 flood that had just passed when we arrived there in March of 2016. And then lower down, we have another somewhat coarser event that seems to correspond to the 2011 flood, which is the flood of record in this particular area. So we think these cores are able to tell us something about when these floods are happening in the past. So this is just the upper 20 centimeters. This core goes back, 200 more years and can tell us more about events in the past. We have other cores that go back a little bit further and essentially allow us to reconstruct when flooding happened over the last 500 years or so. We also think that these events can tell us about these deposits can tell us about how big those floods were, so what their magnitude was in quantitative terms. So what we've noticed is when we looked at the coarsest part of those deposits, there are differences in how coarse those are. Some are coarser and some are less coarse. And so just by basic hydrodynamic theory, we can assume that a faster moving flow, a higher discharge, is going to be able to mobilize coarser material. And so we would expect, barring sort of all the realities of the real world, in a very simple system, that that the coarseness, the texture of these events is going to be related to the discharge that entrained them. And so what we found working on the Mississippi and what Willem Tunen published first working on the Rhine is that there is this pretty nice linear relationship between sort of a normalized grain size score, that's showing on the right, and the discharge of historical floods, right? So these are all historical floods where we see the event in the core and we know what the discharge was because there's a gauging station nearby. And we tend to find this nice linear relationship. And so if we're careful about where we pick sites, we try to pick sites where there hasn't been a lot of lateral migration. We can have a reasonable amount of confidence that we can then use this relationship to reconstruct what flood magnitudes were going back in time. And so we've done this now. We published this last year. We did this for three sites on the lower Mississippi, Lake St. John, Lake Mary, and False River Lake, with notified here is STJ, MRY, and FLR. And then we also looked at a tree ring site. This is using flood rings and tree rings. I don't really have time to talk about it, but my colleague Matt Therrell at the University of Alabama did that piece. I can answer questions or refer you to other literature on it if you're really curious. But in essence, these are all oxbow lakes, and we're coring them. We collected a lot of cores from these lakes, but and we use multiple cores to sort of verify that an event is an event. But I'm really mostly just talking to you about the core that we collect that's closest to sort of the plug, because this is the area that's most sensitive to that incoming bed load during flood events. So when we look at all those events together, all those records together, we get this very messy looking plot that let's spend some time sort of deciphering. So on the x-axis here, we're looking at time going back 500 years, the year 1500 up to today. On the upper panel, we're looking at the flood frequency, so the number of events that we see in a 31-year moving window, right? So, you know, just literally, again, a count of how many we see. And there's different lines and different colors to denote different sites. And then the red line is showing us just the stack, the average of all of the sites. And the black line is showing us the instrumental records, so what we know happened from the gauge at Vicksburg. The bottom panel is showing us the magnitude of those floods reconstructed. And so again, they're color coded again by the site that they are. And again, black is the instrumental data. So with any reconstruction like this, the very first question we need to ask is, are we doing a reasonable job of reconstructing this process that we're interested in? And so what we did here, and the way to do that is to compare your reconstruction to what we know happened, the instrumental record, right? And so that's what we're doing on the right here. We're looking at just the last century or so, and we're comparing our reconstruction in red, the average of all, to the instrumental data, and that's in black again. And so in terms of frequency, we're doing a pretty good job, right? Some sites are more sensitive than others, but the average of all those sites is pretty good. We're very highly correlated in the instrumental record, and we're clearly just capturing those trends quite nicely. In terms of magnitude, that's on the bottom panel. Again, the general trends, we have decades when floods are generally bigger and decades when floods are generally smaller. We're sort of capturing those trends in general, but the uncertainty of our reconstructions is still pretty high, and that's something that we're working on trying to improve. We also our estimates tend to be very conservative because we're using linear regression, and so we tend to sort of overestimate small events and underestimate really big events. And that's, again, because we're using regression, and again, we're trying to think of better ways to do that. In general, I think we're doing a pretty good job, and I think we can use this information to say something, which is what I'll do now. All right, so let's go back to our sort of long-term view going back 500 years. There's really two trends that I want to point out here. The first trend, when we look at frequency and magnitude to some extent, is that we have these sort of multi-decadal oscillations in frequency and magnitude. So we have, you know, periods that are several decades long when floods are more frequent and or bigger, and other decades when floods are less frequent and smaller. Right? And the other trend I want to point out is that over time, especially over the last century or so, the frequency of flooding has increased fairly significantly, as well as the magnitude of those floods. So let's break down those two trends and try to understand what's going on with them. So the first trend is those multi-decadal oscillations. Here, that's what we're showing on the black line on the bottom of the panel, again, going back 500 years. This is our flood frequency you just saw a minute ago. And let's compare that to what's going on with ENSO in the tropical Pacific, so the number of El Nino events, as well as what's going on in the North Atlantic. Some of the drought literature has shown that the North Atlantic is sort of has a secondary role, but is also important in sort of modulating aridity and moisture into central North America. And so what we see is that both of these, both Atlantic sea surface temperatures and tropical Pacific sea surface temperatures, are really highly correlated with this flood event frequency. Right? And so this supports some of the inferences we were making by looking at some recent historical floods, and it supports what the simulations are showing as well. Right. The other thing that we were looking at that we're interested in that trend was that increase in flood magnitudes and frequency to some extent that has happened recently over the last century or so. And so we tried to address that and try to understand what's going on there by doing a very simple attribution analysis that really just uses regression. And so to understand what's going on here, again, we're plotting out the last 500 years of flood magnitudes. Each of these gray dots is a flood. And the red line here is just saying, what's the largest flood of the previous century? So if you were standing in the year 1600 and you look back 100 years, what would be the largest flood that you saw? And similarly, if you're standing in the year 2000 and you look back 100 years, what would be the largest flood that you saw? And this is kind of a simple way of thinking about the 100-year flood. We can also go ahead and just calculate what the 100-year flood was for 2 periods, what we consider sort of a baseline period before 1800 and sort of the modern period about the last century or so. And when we do that between the 100-year flood, we see that there's about a 20% increase in that magnitude of that 100-year flood. And so the question is, of course, what's driving that? That's that same trend we were talking about before. So what we did was just build a very simple statistical model that tries to predict, just based on those natural modes of climate variability, what we would expect from the 100-year flood, what we would expect it to be in a world where flood magnitudes were only driven by just natural modes of climate variability. And so what we see when we do that is this blue line, right? That statistical model is trained on the year like 1500 to 1700, and it's doing a pretty good job of following what we observe, right? The red line and the blue line are similar up until the early 20th century, and then they really sharply diverge. And we see that again when we look at what we predict in the modern period for the 100-year flood in this world where only natural climate variability drives things. We only expect sort of a 5%-ish increase in that 100-year flood. And so what is driving that? Well, this analysis, again, is pretty simple. It's not really sophisticated. We're not looking at details about what specific drivers, but it's not climate, right? It doesn't seem to be at least natural variability of the climate system. And so a really obvious thing to point the finger at here is all the changes that people have made, especially beginning around the early 20th century, to the channel, the floodplain, and the basin itself, right? We've converted much of the basin to agriculture and urbanization that changes runoff regimes, and we've channelized the river. We've decreased the size of the floodplain, especially in the lower Mississippi, significantly. This is also true of the Missouri and the middle Mississippi. And so all these effects are serving to amplify flood hazard, to make the floods that we've seen over the last century or so bigger than anything we've seen in the previous 500 centuries. And this follows, again, really basic hydrologic theory and hydraulic theory that's been well known for over a century. But it's just nice to show it with this paleo data and get this long-term perspective on it. All right, so sort of wrapping up here, and the topic here was all about 2019, and so how do we apply what we've learned to today going forward and to what we know about the 2019 event? Well, I'd say that the pattern of flooding that we just observed in 2019 really fits nicely with this pattern of flooding that we expect, at least based on historical data and paleo data from an El Nino event. And so when we look at the pattern of flooding that we observed in 2019, we're looking at flooding along the upper Mississippi, the Missouri, the Arkansas, and the lower Mississippi, basically the entire western half of the basin. And that's really consistent with what we expect in terms of soil moisture during an El Nino event. That's what I showed you right at the beginning of the talk. And sure enough, back about a year ago, we entered into sort of a moderate El Nino phase that lasted through the entire winter. Now, there was a talk last week on Monday, a really great talk that looked specifically at winter precipitation in 2018, 2019, and in relation to ENSO in part. And they concluded that the patterns associated, the precipitation patterns of this last year really weren't consistent with your sort of typical El Nino. And so I'm not entirely sure how to square our observations with that analysis, except to say, of course, that each flood is different and each El Nino event is different. And there's been some literature lately exploring this concept of different flavors of El Nino and how different flavors of El Nino alter the teleconnection. And so that seems like sort of a promising way forward in terms of improving our ability to forecast, is really trying to understand this relationship between the tropical Pacific and flood hazard over much of the Mississippi basin. All right, so with that, I'll just say thanks to our funding agencies and all the people who helped us with fieldwork and lab work, as well as my collaborators whose smiling faces are here. Okay, thank you very much.
Thanks very much, Sam. It's really interesting. I'm really fascinated with the way that you've brought together that paleo perspective and then integrated and separated out the climate and non-climate stressors to the system. That's a fundamental concept that we emphasize when we teach people about climate adaptation planning across a whole suite of climate-related hazards. So it's a really great case study. We're going to move on at this point, in the interest of time, to Jerry Galloway, who is from University of Maryland, and he's going to bring his perspective about flood planning And as you can tell from the title of his talk, he's going to challenge us to consider really what we can and can't do. Thanks, Jerry.
Good. Do you have the, can you see my slide?
Yes, you're,
Okay.
and we can hear you clearly.
Great. Well, I'll start off. I really got to say that I've enjoyed both of the talks before me. The paleo one links back into what I'm going to talk about a little bit, and raises lots of questions for me who have spent their last 50 years dealing with the Mississippi and trying to figure out just those sorts of things. But let me go through and say that I'm not going to talk about planning very much. I'm going to say that it could be the fault of hydrologists, meteorologists, and climatologists that we have all these floods. But I'm not sure that's so either. So if I go back to my hero, my mentor, is a person named Gilbert White, who was a geographer at the University of Chicago and then ended up in Colorado. In his dissertation, which he finished shortly after being interred by the Germans during World War II, he came back to the States, finished his dissertation, and it was all about floods. And he made this rather fundamental comment. Today, Gilbert would say acts of the human race or some other term, but he was very much pointing out that while we were doing a lot to build things, we were not doing very well in reducing the losses. So what I'd really like to do is talk about random thoughts on how we can dampen the effects of too much water. Why the water gets there, we can talk about that. I'm not going to do that today. My story begins in 1993 when we had the flood of that year, and I got a call to come to the White House, and I was told, I wasn't asked, I was told what you're going to do is get a team of 15 federal employees together, and you're going to decide why the flood occurred, what we should do about it nationally, and what challenges exist for the future. And I'll quickly go through these, but my idea is to throw out things that are still bothersome and that really deal with some of the comments made by Sam in the last talk. Is why is this happening? What are the factors that make a big difference? And I've just finished spending 3 years in Texas looking at the aftermath of Harvey and some of the minor things that might come from the same thing. 6 months after we showed up in the White House, we came out with this report that did answer all three questions. The interesting part, the major conclusion was this. When I took this into the vice president and Dr. Baker, who was the head of NOAA at the point in time, the vice president said, "What do you mean?" And I said, "It rained a lot." And Dr. Baker said, "That's right on the mark. That's the problem. When you get too much water in a river, it floods." The vice president, however, had used this slide that you can see here to show the sixth Great Lake, which was the intensity of the soil wetness in western Iowa and Nebraska, and when we're dealing with Minnesota and places where there are challenges from that particular flood. The second part of that was major floods are going to continue to occur, and yeah, there we go. And people and property are going to remain at risk in the floodplain. It is a difficult challenge to deal with this, and most residents don't understand what it is. We also said that many structures are unnecessarily located in the floodplain. Obviously, it isn't going to get any better, and this was not much of a prediction to say that we're going to grow between 1993 and the future, and that climate change, then we called it climate variability for some, and that uncertainty would have major impacts that we really need to deal with. You don't need my income tax, but it isn't going to get any better. Somehow I'm whipping this thing up here. Okay. Human activity caused significant habitat loss. I will comment as we go through that the challenge is I haven't heard many people talking about the impact on the environment of the recent floods and the things that have been done since 1993 that will cause them to be exacerbated or mitigated. And we're not working very hard on that. We know flood insurance participation is poor. We told that to the leaders, and it turned out that it's worse now. Management of floodplain activities is diffused. All of this is to get to Gilbert White's thought, why are we having this happen? We know where the water is going to be. We've got some people that are brilliantly figuring out how we might learn when it's going to come. But even when we know it's going to come, we're not dealing with the issues that have to be addressed. And so we ended up after 93 with a light flood in 95, 97, much like this year. The big floods were in the lower Mississippi, the lower part of the upper basin, and in the Red River of the North, where Grand Forks went underwater, and we have this iconic picture of a big flood. 2001, more floods in the Missouri, Mississippi. 2005, of course, was Katrina. It's got nothing to do, it has something to do with the Mississippi. But by and large, what we learned from this was that we are not taking care of our levees and structures, and that infrastructure plays a large role in dampening flood losses over time. And we're still wrestling with that bear in that part of the basin. Then 2008, we had again the flooding. This is the Cedar River, and you can recognize Cedar Rapids, Iowa City, all the places where we had flooding, again, much like we've talked about. And then 2011, and for those of you who don't know, that is a nuclear power plant surrounded by water but not flooded by water. And New Orleans, with the levee being, the top of the levee being lapped at by the waters passing by on the Mississippi. So 2011 was a big event. And then, of course, we have the junction of the
We seem to have lost you, Jerry. If you can hear me, you may have gone out of cell phone reception, or something else has happened to you. Can any of the other panelists hear Jerry?
No.
Nope.
Okay. Well, we may need to move on and come back to Jerry, and we can come back to that slide. In the interest of the audience, let's do that. Doug, if you could step in, we'll do your talk, and we can come back to Jerry, and he can pick up in 2011.
Sure.
If he dials back in.
You bet. Okay, show my screen. There we go.
Thank you, Doug. So Doug is the Regional Climate Service Director for the Central Region.
Here I am back
for NOAA.
Oh, he's back.
How long have I been
Oh,
off?
you're back. Well, when you got to the 2011 slide, you cut out after talking about lapping over the levees, or maybe laughing at the levees. I wasn't exactly sure what you said, but
Okay.
now if you'd like to pick up from there, you were on the 2011 slide.
Yeah, let me see if I can get me back on there. There we are. So let me just go from here. We've had lots of floods. I've got 5 minutes and 44 seconds, and I'll be finished. We've got a different world around us. Let me just say some of the things I think we need to worry about. I was asked to talk about socioeconomic. We have all of these issues. Population, pressures for development, crumbling infrastructure, which is a problem. We found out that in 2005, we had major problems with our levees, and we haven't done anything about it. We've got fiscal challenges. There's no infrastructure program. We have ineffective flood risk management, where we're not linking up the flood risk management issues at state, federal, and local levels. We have disasters occurring, and we're not very resilient to them. And we live in this very interesting VUCA world, volatile, uncertain, complex, ambiguous situations. And so we have to deal with that. What do we need to deal with? The challenges are, I think, admitting to climate change that we have it, understanding risks, defining what we're trying to do. You ask somebody, what is the program that you're trying to implement for flood damage reduction in the Midwest or in the South or anywhere? What is the goal? What is the standard you're trying to deal with? And what is the plan that you need to deal with this? Where's the funding coming from? And something that's not talked about very much is the social equity, because the programs we have now tend to disadvantage those of low economic strata. And compared to our friends in the Netherlands, we don't have any national will to move ahead with flood damage reduction or loss prevention. Again, how do people see this? Is the global risk landscape from the World Economic Forum. You can see all the different risks. Farther to the right, the more likely it is to occur. The higher up is the more extreme it will be. And what we see here, when you get down to it, the big one is extreme weather events, natural disasters, failure of climate change, and water crises. So where water goes, we have these really big risks to deal with, and we're not dealing with it. You know about the climate change bears better than I do, but uncertainty is what gives me as an engineer and a designer a challenge to figure out, how do I build something for 50 years from now when the scientists can't tell me what the level of the sea is going to be, or the level of the river is going to be, and how much it's going to change, because you have to start building something today. We started off, and you mentioned earlier, the MR&T, Mississippi River and Tributary Project. This says that in 27, they did come up with a plan for the lower valley, and it has worked rather successfully since 1927. The 2011 flood was the first really big test. The 93 was not. In comparison, the 2011, coming out of the Ohio River in the large flows that were coming down the Ohio, was a problem for the country. It was a problem for the lower valley, and it passed with, I would call it, flying colors. So there was a plan, it's been implemented, and people are dealing with it. It doesn't say why and how we can change things, but it is working since 1927. We've come up with all sorts of other plans to deal with other parts of the country that have problems, especially the Upper Mississippi River Comprehensive Plan. But what do we have? We have a Missouri River Basin where the only coordinated action is the action on the 6 dams that are on the Missouri, and they're regulated, and they are, to some people's feeling, not really doing as much as they could, but their only thing that is the one agency has been given responsibility for, the Corps, to deal with that. You can look at the problem of having these dams. What about all the tributaries? What else goes on in there? What about all the problems you have with building a program in other places? Very difficult. And there is no comprehensive Upper Missouri or Missouri program for the country to deal with. The same thing would apply to the Upper Mississippi. We have all these locks and dams. They give you some interesting challenges, but the tributaries tend to be the larger challenges, and we don't have a comprehensive plan. And it's all each is done by individual organizations or entities. Somebody is taking me off.
We jumped out to a URL, so you need to switch back to your presentation, I think.
Okay. Yeah.
You'll have to switch applications back to PowerPoint, I think.
Right. Not.
Okay.
Yeah, there we go. Okay.
Yeah, there it is. So you'll need to go to that other window where it's already presenting.
Yeah, let me go over here.
If you bring your mouse to the bottom.
Yeah.
There it is.
Okay. Quickly, let me go through. We have the problems of the failed levees. We've done nothing about the 50,000 miles of levees we've got, not doing very much to figure out what were happening. We don't have the money allocated to dealing with this. Social.
Oh my. Seems we are plagued by some technical issues with Jerry's presentation. Given what happened before, let's give him another 10 or 15 seconds to join back in, and then we'll jump back to Doug. I have a good question brewing for Jerry if he does join back in. So it's almost the top of the hour, and it's a good time to switch over to Doug. And so, Doug, we'll make you presenter, and we'll give Jerry a chance to answer questions after your talk.
Okay.
Doug is a close colleague here at NOAA, and he's Regional Climate Services Director for the Central Region, actively working with people all over the federal government and in private sector to understand climate information. So thank you, Doug, for bringing your perspective about the impacts of this 2019 event, which, as you note, are continuing to this day.
Right. So thanks a lot, Ned. And you're going to see here that a number of things I'm going to talk about reflect or parallel some of what Dennis said and what I think it's General Galloway also commented on. Yeah, let me just go on here. Just to kind of put a perspective on this, and I'm going to probably go through a couple slides fast because Dennis stole all my thunder anyway. But annual precipitation across the upper part of the U.S., actually across the central part of the U.S., we can just say it that way, over the last, let's say, 30, 40 years compared to the first part of the century. As you can see, wherever it's green there, we have seen increases in percentage of precipitation. So things are getting wetter, right, generally. This is a general concept. This is from the National Climate Assessment. As are both of these graphics at the bottom, one showing trends in flood magnitude on the left, increasing mainly, again, in the Missouri, Mississippi basins, and then on the right, the frequency of heavy precipitation events has also increased. Now, all three of these graphics are sort of what I would call reality. In other words, there's not, these aren't climate change graphics. These aren't saying this is what's going to happen in the future. This is already what is happening. Okay, that's important to think about as we go through this. So again, Dennis showed a map similar to the one I'm showing here on the right in terms of record rainfall. This is just looking back. This map, anyway, is looking back over the last 12 months, ending in August of this year. Every place it shows that dark green color is a record out of the last 124 years in terms of precipitation. For that state, they've reached a record. And actually, that first statement up there, as of August, oops, back up. As of August nationally, we've had the wettest 5th, 7th, 8th, 9th, 10th, 11th, 12th, 18th, 36th, 48th, and 60 months on record. So nationally speaking, across the entire nation, all of those different time increments, we've had record rainfall. Okay, that's interesting, right?
Just in this year. Is that what you mean?
Well, from now back 5 years. The last 60 months, it's never been wetter than the last 60 months. Never been wetter than the last 48 months. Never been wetter than the last 30, etc. Okay? Does that make sense?
Got it. Yes.
Okay. All right. So here is just a list of some of the places that you can see here. All these locations listed on the left part of the screen. Fort Smith, St. Louis, Topeka, blah, 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 down to Toledo. Have never been wetter. All those cities. Below that are sort of the second tier, second wettest for all these cities. They may end up at the end of the year being the wettest. But what I'm trying to show you here is, golly, that's a lot of cities. And if you look at it from a national map point of view, those large triangles show you the location of all those cities, as well as where some of the second and third wettest cities are. And you can see they're fairly concentrated in the center part of the country. Not a surprise there, right? You can also see some dry areas and warm areas off to the south and east where they're having some drought issues as well. So communicating risk, I want to make a point about this as well. You know, Dennis mentioned earlier about webinars that we do that pretty much focus on the north central part of the U.S. When they say central region, that means basically Wyoming to Michigan. That's the north central part of the U.S. that I work in, and Dennis works in a large part of that as well. What I wanted to show here is that this is after the big bomb cyclone and some of the initial flooding, but long before this, we and the Weather Service, especially the hydrologists in the Weather Service, were communicating, gosh, these conditions are sure wet this year, and it sure has been cold, and all these other issues that are sort of that kind of accumulate that could cause some issues later this year. Now, so we were relating this information, which I think is important. Dennis mentioned the webinars, and again, put a plug in for myself here. If that's something you're interested in, focused on the north central part of the U.S., write me an email, doug.clark@noaa.gov, and I'll put you on the list, or I'll send you information that you can get on. We do these webinars, we do quarterly briefs, we do put sort of climate level, multi-month summary and outlook kind of information out there to give people a clue. Now, did we have a clue that it would be as extreme as it was? Heck no. I mean, that's why it's an extreme event, by the way. Very, very hard to predict and see in advance. However, the probability certainly was there. Were certainly increased this year for such an event, but no one's going to usually go out of their way to predict those kinds of things. So anticipation of record flooding definitely wasn't in the cards, especially at the levels we got or have. So now I'm going to show you a bunch of different pictures. This is in the Platte River Valley near you won't know where this is probably unless you're from Nebraska, but between Columbus and Schuyler, Nebraska. This is a friend of ours who lives down by the Platte River, and this is part of indicative of the damage you see across Nebraska in various in March, in various places. But it's also indicative of the kind of damage you get, or we have been getting, in many river basins across the Midwest this year. Things like this upper left-hand corner, or left-hand corner picture is a road that's pretty much it's a gravel road. Was a gravel road, and then you see these big divots in the field, and this is a pretty shallow one compared to what they can be on like Missouri could be 10 or 15 feet deep in some cases. You also see sand kind of redistributed in the Platte River. If you know anything about it, is a sand-based river, but the land around it is used for crops, for grazing, and all that other stuff. Well, as soon as you put a foot, 2 feet, 3 feet of pure sand on top of all of that, or you wash away, in many cases, a lot of that topsoil, you're left with pure sand, which isn't as great to use agriculturally, that's for sure. And then you see it sort of some infrastructure issues. I used to go down to this farm actually and fish and do other things. So anyway, more pictures from around there, more sand, more, and lower left, unfortunately, some dead cattle, which was also a huge issue across Nebraska when the bomb cyclone and all the flooding occurred. And then you see the redistribution of all the sand in new lands there. These are more recent the top picture is a picture of a fellow who's in a corn crop. I think that was earlier this year or last year, and there he is in a kayak, and you can just see the tassels at the very top of that. So they've seen severe flooding in this is up in South Dakota, where along the James River, which has seen record levels as well, but again, indicative of some of the issues facing agriculture and such. The bottom pictures are on the left, a new sandbar, if you will, in the Missouri Basin. And if I don't attribute things, they're pictures I took. You can use them. I don't care. If anybody ever wants them, let me know. And the picture on the right is a new channel. Actually, that's running water through a farm field in the Missouri Basin bottom as well. Floodplain, I should say. This is just giving you a perspective, I guess you could say, of some of the damages in terms of harvested crops from last year. And again, we're down in the Missouri floodplain. The picture up in the upper left is actually from a different place, but I want to give you an indication that if you're not from the Midwest and you don't know, a lot of times they pile up mainly corn outside. Sometimes they can cover it, sometimes they don't. But anyway, all that corn's piled up there to be shipped later on a train. Well, that's a pretty common sight when you have great yields and a lot of production in a particular year. And then down below that is a picture of a grain bin, that was storing corn, and because it got wet, the corn expanded and burst. And I have several pictures of those, again, south of Omaha, north of Kansas City, where basically people's livelihoods have gone up in, I don't know what you call it, gone away on the flood. but as soon as you get wet, corn this wet is worthless, and so you have to do something with it. Thus, you go to the pictures on the right, and you see at the bottom right picture is earlier this year. I took a picture, I think, of this elevator in the Missouri bottom, and they weren't doing anything at the time, but the water was all around it. Well, by the time I came back in early September, they were burning it, because that's basically all you can do at this point is burn that grain that was sitting there. So you can think of the millions of dollars that were lost along those, just with those types of damage. Transportation woes, of course. This map on the upper left shows, basically Rockport, Missouri, all the way up into Iowa. I didn't put the whole map in there, but it just gives you an indication of all the road closures. That's an interstate that goes up to the middle of that, I-29. This picture on the lower left is very recent. That's flooding in South Dakota. I think that's I-90. Picture lower right, also in the Missouri Basin, more issues with long-lasting transportation issues. A lot of hardship there. And then kind of just more sort of random shots. That's Interstate 29 again on the bottom, lower bottom center. All those industries or shop or businesses and such underwater. Platte River breaching a levee here across or near Plattsmouth, and this coal plant was not affected. Obviously, the house was, and you see that all over the place if you drive I-29 up through Iowa and Missouri. Then recently, a picture from Mike Wilson at USDA. He was flying into Omaha. This is still going on. He took this pretty recently. There's a lot of water still in the basin, a lot of damage still going on. And then I want to kind of give you a summation of where we are in terms of the Corps of Engineers and how record-setting this year actually is. The red line is this year, and these are sort of system storages. So this is looking at all the reservoirs across in the Missouri Basin, and I think General Galloway mentioned 5 of them or 6 of them anyway. Here's where we are compared to the record year. 2011 was the previous record year. That was a bad flood. And then 2018 was last year, which was not shabby. The average you can see is way down there. This sort of dashed-ish blue line is normal, if you will. I'm not sure there is such a thing anymore, but we're well above any record level for this time of year than we were or have been in the Missouri Basin. And now I want to show you the last sort of graphical thing that I have here is this is 2019, furthest to the right. That's where we are right now. This is an average runoff prediction at Sioux City, Iowa for the Missouri Basin. Pretty amazing that only 2011 is this other peak over here, and that only 8 years later we have another similar peak. It's going to be interesting to see which one ends up being the higher year, I guess. Again, last year wasn't shabby in terms of runoff, very high runoff last year. I think that was, until this year, the 3rd highest runoff year last year. Now it's 4th. So you can see back through time that we've had high runoff, but more and more higher peaks. A lot of variability, but higher peaks more recently in the basin. So what are the implications? Sorry, what are the implications of all this water being in the basin now? The reservoirs being very full now. Soil moisture being very high across large portions of the basin. Well, one thing is that the Corps is going to have to release a lot of water because they need to get down to a certain level to be ready for spring, right? So they're getting in there sort of under the gun to do that before the rivers begin to freeze up and they're not able to do so. Okay, so there's a timeline there. When we have big rains like we have been having over the last month, it doesn't help much. And in fact, it hurts. And so that's why you see sort of these lines these lines sort of staying up here when we would hope there would be a much faster recession on how much water is stored in those reservoirs. But because of heavy rains and more runoff, they haven't been able to do that. That also leads to challenges with levee infrastructure and field repair. Farmers will try to, and Dennis can probably talk more about that if there's interest, how to deal with fields that have been either eroded away or sand piled on them, and it's not a cheap thing to do. There's a lot of infrastructure. I showed you some transportation issues that are going to be underway for a long time, and the excess water around them is not going to be helping. Also fixing levees that were broken, that have been broken, that's going to take a long time as well. Going into next spring, winter and spring, actually, there's an elevated concern, I would say, and potential for more flooding, especially if we get average or above normal precipitation. We're going to have very high groundwater levels, which will affect a number of people in various places. And the one thing also that was mentioned earlier about ecosystems, there are both positive and negative impacts to that. I've never seen more, I guess, cranes and herons out in these flooded fields I've ever seen. I've heard record reports of various frogs and other animals in Missouri anyway, and I'm sure that's everywhere where the water has been high. So I say positive and negative. Obviously, there's negative ones too. A lot of animals die in those floods and such. And then finally, or not finally, but almost finally, diseases, various human, animal, and plant diseases could be a factor, especially next year as fungus, mosquitoes, that kind of thing could cause issues. And then finally, as Dennis probably noted, harvesting this fall could be an issue. Storage this fall could be an issue, and drying grains will all be issues that are going to lead into next year for sure in a large part of the center of this country. And that's all I have. Thank you.
Thanks, Doug. Do you mind, would you please put on screen I think it's slide 13, the one with the storage through the year, because in some ways it ties together at least the last three talks. Yeah, no, you were on the right one. Where we see
over the years?
The storage.
Or
one
this
with
one here?
This one, please. Yeah. So I have
Okay.
a question about that because I think implicit in this are some engineering constraints that Jerry was alluding to before he got cut off, and also some of the implications of Sam's work. And so I'm going to try to articulate this into a simple question, but what I'm seeing in this is that the storage at the various reservoirs changes throughout the year. And my first question is, I'm assuming that is in order to regulate flow in anticipation of the anticipated precipitation and runoff. Is that roughly right?
Correct.
Storage has to,
it's a
okay.
Yeah, it's a rather complex issue in the Missouri. There are eight authorized purposes, and I won't go into that because that's a different talk.
Okay.
But I will say that the Corps has responsibility in various ways of keeping enough water and not enough water in those reservoirs for flood control, among other things. So there's a sweet spot. So there's a sweet spot that they're trying to reach every year, this time of year, especially this time of year.
Well, so my question is the sweet spot changing because, as Sam pointed out, the engineering itself alters flood frequency. And as Jerry pointed out, we need the engineering in the whole system, both levees and dams and so forth, to protect property, but it's also got the feedback on the system of changing the flood frequency profile of the river system. So
correct.
Are people talking about this feedback in terms of reanalyzing the engineering of the system?
You bet. People talk about that quite a bit, and there's a lot of interest in that. There's a lot of interest in understanding sort of, if you will, climate change and variability aspects of that. The Corps has worked with NOAA on a number of occasions to better understand that. it will take something, changes to the master manual, which is, again, a different talk that I can't give, to sort of implement those things. And really, if anybody out there is listening from the Corps, please forgive me for saying the wrong or getting it wrong. But there would have to be some, I guess, I call them policy changes that would have to happen. So, but the fact that the Corps and the weather and the NOAA are talking, among others, about these things is at least a first step in terms of basing it on science once we get there.
This is Jerry. I would just point out that in 1988, we had the drought on the Mississippi, and that caused the master manual revision to begin. It has not been completed. The courts have taken over. You mentioned the 8 different purposes. The Congress has told the Corps to restudy that, and then they cut off the money to do it. It is really a difficult issue because it's policy steeped in politics and upstream, downstream. The other thing is the different projects you have, including the 7 or the 6 main stem reservoirs, only can do so much. And in 2011, they ran out of room to store. That's always been something that has been known to people who looked at it. But once you get to that point, it's an uncontrolled discharge. We're fortunate this year that you didn't have that because they could control it to a degree. You all, with the weather, have the upper hand. And it's going to be interesting to see how the policies shift as we begin to recognize what climate change and what we're learning. We used paleo in 1993, but nowhere near with the technical expertise that we have now. So there are things that make it positive for the future, but it's not going to be simple.
I'll say one more thing that follows on to that if you look at this graphic and you can look back to March and April, there was there was an uncontrolled from the Niobrara River and the eastern South Dakota rivers, as well as all the Nebraska rivers, were contributing in a fairly lower basin, uncontrolled. So the big reservoirs didn't come into play earlier this year when the first major flood hit. And unlike 2011, where you see a big peak that goes way up high there, it hit hard early. Again, lower basin, no reservoirs in the way, if you will. The water came down freely, and people didn't have nearly the time to adapt, to get the machinery out of the way, get their cattle out of the way, etc. It was truly a big disaster. So
it seems like you had this really steep rise at the end of March, and then a steep rise at the end of May as well.
Right.
But then you also need to recognize that one of the changes we're seeing in precipitation is an increase in fall precipitation. So you're seeing these bulges in the fall, which is at the end of the period when they're able to release additional water. So you're trying to play catch up late in the season when you don't have a whole lot of time to deal with. So we have a changing precipitation profile that the Corps is also trying to hit in all of this process.
All right. Well, that's a really good note to end on for us in our office, because it's those changing precipitation profiles we want to bring more attention to. That was Dennis, correct?
Correct.
All right. Thanks for chiming in, Dennis. Our speakers today have been Dennis Toddy, Sam Munoz, Jerry Galloway, and Doug Cluck. I want to thank all of you very much for participating in our webinar. And we will stay tuned to this ongoing event and the way that you all are contributing to our nation's response. Thanks very much.
Thanks. Can I ask a quick question?
Yes.
Yeah, so you're going to put this online for future use, right?
Yes, it's being recorded, and we will post it I've already posted the URL, but I'll show my screen and show everyone where to find that.
Great. Thank you.
Okay, that's a good point. And so here I am. I'm showing my screen, and the Climate Program Office website is cpo.noaa.gov. I'll put that in the chat window. And if you go to the news section, I'm clicking on it right now, and scroll down, you'll see at the top a highlight for our webinar series, but you can also load 5 more articles here and scroll down. You'll see this is part 1. There's a link. And then part 2 will be right here. Okay, so not too hard to find if you go to cpo.noaa.gov and go to the news section. We'll be uploading that within the next day, I would say. So thanks everyone for participating, including the audience who've joined in, and we will be in touch by email with more information about the recording. Goodbye for now. You're welcome.